The point O in the middle there is equidistant from each wire. The magnitude of the magnetic field due to the wire X alone at that point, so that's the top wire, is equal to B Teslas. Oh dear, algebra. So the magnetic field at O due to all three wires at once would be which option? Now let's think about this. If wire X creates a field of B Tesla, which direction will that be in? We can use the right-hand rule to see that it'll be going into the board. So that's the magnetic field due to wire X. And it'll be a strength of B Tesla. So what will be the field from wire Z that goes vertically? We can use the right-hand rule to see that it will be coming out of the board. And it will also have twice the magnitude of the force from wire X. Finally, we can look at wire Y, and once again, we can use the right-hand rule. We find that it's going into the board. And so it'll have the same magnitude as wire Z. So if wire Y and wire Z have the same magnitude, and they're moving in opposite directions, then they're going to cancel out. And of course, the only wire left that's still acting is wire X. And we already know from the question the magnitude of wire X's force. It's B Tesla. So our correct answer is B Teslas into the page. Question 2. A metal wire, a meter long, is placed onto an electric balance such that it is horizontally at rest. Following so far? The balance records the mass of the metal wire as this many grams. A second wire is placed just above the first wire, just 2 millimeters above it, and parallel to the first. So now you have two wires and one of them sitting on the scale, and 10 amps of current flow through each wire in opposite directions. So what is the new reading of the balance? So here we have to figure out whether the top wire, the one that's suspended above it, is going to attract the bottom wire and decrease its apparent weight, or repel the bottom wire and increase its apparent weight. So right away we can see that because they're flowing in opposite directions, they're going to repel each other. That means that the reading on this scale is going to be bigger than what we started with. So it won't be D, and it won't be A, because A is just the same. Then we can use our equation to find the force, which looks something like this. That's a force per meter, but we're only using 1 meter, so it should work out. And we can use that to find out exactly how much the new one will weigh. And it turns out it ends up being 13.5 grams. Instead of 12.5. Roughly speaking, of course. Once you've found the extra force on the wire, don't forget to convert it to what the mass appears to be on the scale.